Okay, class, so let me remind you where we were last time. So we kind of started a second half of the class. So we introduced R as a set plus two operations, right, which were just plus and addition. Oops. Plus and multiplication. Okay. Satisfying certain axioms. Okay, then we were able to derive some consequences from these axioms. And then at the end, we had defined some ordering properties. Okay, so there was a set of positive elements, which is just a subset of the real line, which wasn't empty. And then this, satisfied, so this was the positive elements, and it satisfied the usual properties. So I won't say what they were, but if you added two positives together, you got a positive number. If you multiplied two positive numbers, you got a positive number, and you had this trichotomy where something was either positive, negative, or zero. Okay, so let me say what we're going to do today. We're kind of going to explore more properties about this positive set, and then see what else we can derive from this. Okay? Maybe I'll make one remark before we go on, which was that before we had defined P, the set that we had defined R and the axioms of addition and multiplication could have been just the set of containing two elements. So it could have been the set 0, 1, so that 1 plus 1 is 0, 1 plus 0 is 1, 0 plus 0 is 0. I won't write it all out. Well, I guess I will. 0 times 1 is 0, 0 times 2 is 0, 0. 1 times 1 is 1. Okay, so you can check that this set of two elements plus these binary operations would satisfy every single axiom that we had, except for the fact that now once we have P, so P ensures that 1 plus 1 is not 0 in this set, okay? Because this is a positive element. Well, in fact, I'll just say it's non-zero. It might have to apply it to its inverse. This is non-zero, and it's in P. And therefore, this would have to be, this is in P, okay, by the property of positive numbers. So it's an important thing to kind of keep track of what these axioms and properties are giving us. So you can think, like before, we really didn't have much, we didn't really know very much about R. It could have been this set. Now that we're assuming we have this positive set that's closed under addition and multiplication, you can get a lot more. Okay, so we'll see that, more examples of that in a second. So let me give you a theorem now, which will just list a bunch of properties that you might expect this positive set could have. Okay, again, it's something that we're going to derive only from the axioms. Okay, so the first one I think I can actually give as a lecture problem. So for every A in R, which is not 0, A squared, which is just A times A, is positive. Okay? The second one says that 1 is bigger than 0. Okay, that's a nice thing to know. And the third is that, well, actually, for any n in n, n is greater than 0. Okay, so it's a reasonable question to say, whether this is, what is n here? Okay, because I defined R as the set satisfying these axioms. I haven't told you, how the natural numbers sit in this set. So n is just going to be 1 plus 1 plus 1 n times. Okay? You can define this inductively if you want, just by saying that 1 in n goes to 1, and then k plus 1 in n goes to whatever, k is, plus 1 again. Okay? I'm not going to get too pedantic about it. So let's see. So let's prove this. Okay, so the first one I am going to just leave as an exercise. And the lecture problem for Monday should basically help there. This one now follows from the first, okay, because 1 is, in particular, 1 times 1. So 1 squared is positive by part 1. Okay? Finally, for the last one, this is by induction. Okay, so you assume, I won't write it out completely, assume k is greater than 0. Then I have k plus 1. This is a positive element. This is a positive element. So therefore, since positive elements are closed under addition, we get that k plus 1 is positive as well. Okay, so here's the first key observation. Okay, I guess I'll just call it an observation. It's kind of remarkable that you can get this just from these axioms. But what we know is that there's going to be no smallest positive real number. Okay, so no smallest positive real number can exist. In other words, there's, you give me any real number, I'm going to find some real number which is positive less than it. Okay? So here's the proof. So first note that if n, or any real number, is greater than 0, then 1 over n also has to be greater than 0. Okay? Because if not, okay, so if not, well then it has to be less than 0. Maybe you can think about or tell me, well, I guess think about and answer to yourself why 1 over n can't be equal to 0. So why not equal? Okay? So then if 1 over n is less than 0, we have that 1 over n times n is less than 0, which implies that 1 is less than 0. Okay? And that was assumed not to be true. So now, if we have any a greater than 0, well, what I can do is, I know that 2 is greater than 0, which means that a half is greater than 0. And I claim that this implies that 0 is less than a half times a less than a. Okay, so let's see why this is. Well, the first part is just because if I multiply positives, I get a positive. And now why is a greater than a half times a? Well, again, it seems pretty obvious. I'll write it out though. So what we have to show is that a times a half times a is in P. Okay, so this is equal to a times 1 minus a half. This is in P. And notice that, well, okay, so I know that 2 is greater than 1, which means that a half times 2 is greater than a half times 1, so 1 is greater than a half. So in particular, this is in P, and therefore I get that the whole thing is in P. All right, so we can always find a smaller real number by dividing by 2. Okay, so now let me make another remark. So as I remember when, at the beginning I said, well, without this ordering property, everything I say is going to be satisfied by the 2-element set. Okay, but now we have ordering, so we can ask, well, what other things satisfy all the properties I've listed? So far, what you can tell is that since we're allowed to divide, n and z do not satisfy our axioms, but q does. Okay, so the rational numbers do. So I can define addition, multiplication, I get all these properties and axioms, I define ordering, I define what it means for one number to be bigger than another, and still we're kind of at the point where the rational numbers satisfy things. So again, we're going to try to lead to getting a definition of the real number. At some point we're going to have to add more properties. Otherwise we might just end up with the rationals. Okay, so let me give one additional kind of corollary, which is kind of useful to show that numbers, that something is equal to 0. Okay, so if a is in R, so that for every epsilon greater than 0, we have that 0 is less than or equal to a is less than epsilon, this implies a is 0. Okay? And the proof is, it is just a true corollary because the proof is, well, set epsilon to be a over 2 if a is greater than 0. Okay, and as we said, if a is greater than 0, we could set this to be epsilon, therefore this would not be satisfied, and therefore we get a contradiction. So a has to be 0 here. Okay, so now we want to kind of notice the main difference between the real numbers and the rational numbers. Okay, so how do you distinguish this? So the main difference between R and Q is called completeness. Okay, what this means is that, roughly, there's no holes in the real line, whereas, square root of 2 is not a rational number. Okay, so it's missing when you draw the line of rationals. Okay? So we're going to need some terminology to make this precise. Okay, to say, what is a hole or the lack of hole in the real line versus, why is this a hole in the rationals? Okay, so here's going to be a key definition. Let, I guess I want a non-empty set in R. Okay, so it's a subset of the real line. S is bounded above if there is some real number, so there is, x in R, so that S is less than or equal to x, for all S in S. Okay, so of course the picture is you have this set S, and out here there's x, and x is larger than each one. Okay, so it's bounded below well, I'll write it out, I guess, if there exists a W in R so that W is less than or equal to S. And then we say bounded if it's bounded below and above. Okay, so let me do an example. So this can just be, so S can be, say, the set of real numbers where it's less than 2. Okay, so this is bounded above. But not bounded, right? Because you can, well, actually, it's a good exercise to think about, why this isn't bounded below. It essentially follows from what we saw for the natural numbers. Okay, so maybe I'll write here, why is this not bounded below? Okay, so you have to come up with a sequence of real numbers that are getting, arbitrarily large in the negative direction. And it essentially will follow from what you've seen before with the natural numbers, but it's a good kind of exercise to write down. Okay? So in this case, so S is here, so there's no lower bound. Of course, there's also plenty of upper bounds, right? I chose 2 because I was trying to be very clever, but, if you're trying to show something's bounded above, you don't have to be clever. Just show it's less than or equal to a googol. Okay, so here is another key definition. Okay, so if S is bounded above, then X is a supremum of S if X is an upper bound for S. Okay, so that means just that X is bigger than or equal to S for all S and S. And this is kind of the crucial point, if Y is another upper bound, then X is less than or equal to Y. Okay, so in other words, we also call this a least upper bound. Okay, so it's an upper bound for S, but smaller than or less than or equal to any other upper bound. Okay, so here, test question. Just test how this is going. What is sup of S in the last example? There's kind of a an answer that people probably naturally think, but you should also try to think, how could you prove that there's no upper bound of S which is smaller than the one that you're probably thinking of. Okay? So it turns out to be 2. And this is why we're trying to, the supremum differentiates between just choosing a googol as a stupid upper bound and 2 as a, kind of smart upper bound. There's also infimums. So if a set S is bounded below, the infimum, or the greatest lower bound is defined similarly. Okay, so here's kind of the first lemma that we can prove about supremums just from the definition, which is that supremums are unique. Okay, yeah, so let me just say everything I say will also be true for infimums, but I don't want to list things twice. Okay? So supremums are unique, so there can't be 2 least upper bounds. Well, the proof is straightforward. Suppose we have x1 and x2 be 2 supremums of S. Well, then we know by definition that x1 has to be greater than or equal to x2, since x2 is a supremum, and x2 is greater than or equal to x1, since x1 is a supremum. So therefore, x1 is equal to x2. Okay, so I'm just going to always call this sup of S and also infimum, or inf of S. Let's see. So here is going to be kind of the fact that distinguishes the real numbers from the rational numbers. Okay? Every non-empty set of real numbers that has an upper bound. Okay, so it's bounded above. So there's an upper bound, has a sup. Okay? And the important thing is that it has a sup in the real numbers. Okay? So that's kind of the crucial thing. If I give you some random set, which is bounded above, you know that it has to have some least upper bound, some supremum. Okay, and that is a real number. This will turn out to not be true for the rationals. Okay, essentially because you can realize numbers like square root of 2 as supremums of sets of rational numbers. Okay? So we're going to see this soon. Okay, but first I want to play around with supremums a bit more. Okay, and show some equivalent statements which will be useful in proving things about them, and then also just some properties that they have. Okay? So let me give you kind of 2 equivalent versions. So some equivalent definitions for x being the sup of S. Okay, so the first one is if Z is less than the sup of S, then Z is not an upper bound for S. Okay, so why is this? Well, if it were, so if z was an upper bound, then x would not be the sup, right? Because z would be smaller than x, and it would be an upper bound, so x would not be the least upper bound. All right, so here's another one. They're all going to be kind of similar sounding, but I promise they will be kind of useful in different situations. So if z is less than x, then there exists some s sub z in S, so that z is less than s sub z. Okay, so this is precisely from part 1. This is 1, just writing down what it means to not be a lower bound, or an upper bound. Right, it means that you have to have a set, or an element of that set which is larger. Just writing down what it means to not be an upper bound of S. Okay, the point is, though, is that now this lets you find elements of S that are kind of arbitrarily close to the supremum, okay, which is useful. Okay, so if I go just a little bit smaller than the supremum, all of a sudden I can find elements that are larger. Okay, so in some sense, there are elements in S which converge to the supremum, okay, which will be useful. So the third one just makes this a little more quantitative. Okay, so it says that if epsilon is greater than 0, then there exists some S epsilon in S, so that x minus epsilon is less than S sub epsilon. Okay, for the same reason, okay? I mean, we're finding arbitrarily close elements to the supremum, which are in S, so this is the z above, okay? So let me do a lemma now. With some facts about the supremum. So x is going to be the supremum of S if and only if. So the first one is just that it's an upper bound. Okay, which we know is a necessary assumption. And the second one is that if y is less than x, then there exists S in S, so that y is less than S. Okay, so this is the same, this is just follows from these equivalent notions, but it's a useful characterization of the sup. Okay? So maybe I'll just draw a picture. You have S, which you don't really know anything about. You have this supremum. Maybe I should just put this warning here because I'm not sure if I made this obvious. X may or may not be in S. Okay, so we don't know what S looks like at all. We don't know if X is in S, but we do know if we go kind of an X minus epsilon away, we'll be able to find some S epsilon in X, or this could be my Y. Okay? Okay, so let me do some examples. All right. Where you kind of can obviously see what this element has to be, the supremum. So the first one is, well, if S is finite, this was, totally valid set to look for? Well, you can prove that S has a greatest element. And so therefore this one is just the sup. Okay, so this is an example where the supremum is contained in the set. Okay. For another example, if you look at the set of real numbers between 0 and 1, then the sup is in S as well. It's just equal to 1. Okay, so the proof is that 1 is clearly an upper bound. And then if you have this element less than 1, there's going to be some element so that V is less than this S prime. Okay, so therefore V is not an upper bound. And I would, as an exercise, just, at least once convince yourself that you can find such an S prime. It will follow, it follows from no smallest element in R. Okay. So therefore, okay, so 1 is the sup. And the same argument works for if I just look at the elements which are strictly less than 1 and greater than 0. The same argument shows that the sup is 1. Okay, so there's an example where the sup is not necessarily contained in the set. So let me give you a couple more additional properties. I'll pause for today. So first is there's a compatibility with multiplication. Okay, or sorry, with addition. And well, we'll see also multiplication. Okay, so if I have this non-empty set inside the real numbers and an element A in the real numbers, then I can make this new subset, okay, which I'm going to call A plus S, just because it's the various elements A plus S for S in S. Okay, so this is just S shifted by an element of the real line. And the claim is that the supremum of A plus S of this new set is just A plus the supremum of S. Okay, so remember this is a set, this is a real number, this is a real number, and that's a real number. Okay, so for the proof, so we know that S is less than or equal to the sup of S for all S in S, okay? And this implies that A plus S is less than or equal to A plus the sup S. Okay, by compatibility of the ordering with addition. So therefore, we have that A plus sup S is an upper bound. Okay, for the set A plus S. Okay, so now suppose that we have another upper bound, so V is an upper bound for A plus S, then V minus A is an upper bound for S, okay? That's easy to check. And therefore, we know that V minus A has to be less than, has to be greater than or equal to the sup of S, right? Because this is a least upper bound. And therefore, adding a to both sides, we have that v is greater than or equal to a plus sup S. Since this happened for every upper bound, we have that a plus sup S has to be the sup. Okay, so since v was arbitrary, we get that a plus sup S is the sup of a plus S. Okay, so there's also compatibility that you can do with multiplication. You can probably guess what the answer is. I'm going to leave it as homework. I have forgotten now whether it is on the individual. I know it's on the group assignment, but I thought it would be on the individual too. Okay, so let me say one more thing. Okay, and then I'll stop here. So we can also apply some of this language to functions. Okay, so what do I mean here? Well, maybe I should be a little more specific. You can have any domain. Okay, this can just be a set. But for the language to apply, the image has to be in the real numbers. Okay? So what we say is that f is bounded above if the set f of d, so the image, so remember this is just all f of x where x is in d, this is now a subset of the real line, so I can say if this set is bounded above. Similarly, you can have functions that are bounded below and bounded functions if and only if the image is bounded. Okay? So maybe I'll just say this, it's bounded if the absolute value of f of x is less than or equal to some constant c for all x in d and c in the real numbers. So I'll end just with one example, which is going to be useful for us later. Okay, so we have, if we have two functions now, so f and g go from d to r, and we might have them being bounded with f of x less than or equal to g of x for all x in d. Okay, so you have two functions, but one of them has a greater value than the other. Then we know that, the sup of f of d is less than or equal to the sup of g of d. Okay, so if you have two functions, one of them always larger, then the sups of the images have to be larger as well. And the reason is, well, for every x in d, f of x is less than or equal to g of x, which is less than or equal to the sup of g of d. And therefore, the sup of g of d is an upper bound, and hence for f of d, so bigger than the sup of f of d. This is just a warning or a note. If you have f of x being less than or equal to g of x for all x in d, doesn't tell you anything about the sup f of d versus the inf of g of d. And maybe this will be an example in a lecture problem where you can construct such an example. Okay. Thanks. Oops.